Welcome. You have nothing to do right now, nowhere to be, nothing to figure out. Let your body settle into wherever you are resting and allow your breath to slow, just a little. Tonight, we are going to drift together through one of the most vast and serene subjects the human mind has ever touched, the deep story of the universe itself. Simply let the words wash over you and let yourself grow beautifully, deeply still. The Big Bang occurred approximately 13.8 billion years ago. That number is almost too large to hold in the mind, and perhaps that is part of its beauty. 13.8 billion years of time unfolding, layer by quiet layer, before this very moment, before this breath, before this night. The universe has been expanding and cooling and arranging itself into stars and galaxies, and you, for all of that immeasurable time. There is something deeply restful in knowing the story began so very, very long ago. The observable universe is about 93 billion light-years in diameter. A light-year is the distance light travels in an entire year, moving at nearly 300,000 kilometers every single second. And yet, even at that extraordinary speed, it would take 93 billion years to cross from one edge of the observable universe to the other. The sheer scale of it all invites a kind of surrender, a letting go of the small worries of the day into something so vast it makes them dissolve like mist. The cosmic microwave background radiation was discovered in 1965 by two radio astronomers named Arno Penzias and Robert Wilson. They were working with a large horn-shaped antenna in New Jersey, and they kept detecting a faint, persistent hiss coming from every direction in the sky. No matter where they pointed the antenna, the sound remained. What they had found, without quite knowing it at first, was the oldest light in the universe, a soft afterglow left over from the earliest moments of creation, still whispering to us across the ages. The cosmic microwave background has a nearly uniform temperature of 2.725 Kelvin. That is just barely above absolute zero, the coldest possible temperature anything can reach. Across the entire sky, in every direction, this ancient light arrives at almost exactly the same temperature, varying by only the tiniest fractions of a degree. It is one of the most uniform things ever measured in nature. There is something quietly remarkable about that, the whole sky humming at the same hushed, nearly frozen note. In 1929, Edwin Hubble made observations that showed distant galaxies are moving away from us. Using the great telescopes of his era, he studied the light coming from galaxies far beyond our own, and he noticed something extraordinary in that light. It was stretched, shifted toward the red end of the spectrum, in a way that meant those galaxies were receding into the distance. The universe, it seemed, was not standing still. It was moving, opening outward, like a flower slowly unfolding in the dark. The universe is expanding in all directions simultaneously. There is no center from which everything is flying outward. Rather, space itself is stretching, and every galaxy is being carried along with it. Imagine dots on the surface of a balloon being slowly inflated. Each dot moves away from every other dot, not because anything is pushing them apart, but because the surface between them is growing. The universe expands this way in 3 dimensions, gently, continuously, in all directions at once, like a breath that never ends. Edwin Hubble measured the recession velocities of distant galaxies by carefully studying how their light was shifted. The more distant a galaxy, the more its light was stretched toward red, and the faster it appeared to be moving away. This relationship between distance and speed was one of the great observational discoveries of the 20th century. Each galaxy was like a word in a sentence, and Hubble was slowly learning to read the language the universe had been writing across the sky for billions of years. The Hubble constant describes the current rate at which the universe is expanding. It tells us, in a single number, how quickly galaxies are receding from one another as space stretches between them. Scientists have measured this constant with remarkable precision, though interestingly, different methods of measuring it give slightly different answers, a gentle puzzle that researchers are still working to understand. The Hubble constant is, in a way, the universe's own quiet heartbeat, steady and persistent, carrying everything apart in its slow, unhurried rhythm. When scientists run the universe's expansion backward through time, the math points toward a single, extraordinarily hot and dense origin point. If everything is moving apart now, then long ago everything was closer together. And before that, closer still. Tracing this backward, like rewinding a slow tide, leads to a moment when all the matter and energy we can observe was compressed into an almost incomprehensibly small and radiant state. It is a thought that can fill the mind with a kind of luminous wonder that all of this, every star and every silence, once shared the same beginning. Let your body settle now, just a little more deeply, into wherever you are resting. There is nowhere to go, nothing to solve, nothing to hold. Let each breath arrive on its own, and let each breath leave without you chasing it. The day is done. Your thoughts can slow and thin, like mist dissolving at the edge of a quiet field. You are simply here, warm and still, and all you need to do is drift. About 75% of all ordinary matter in the universe is hydrogen, the simplest and most abundant element that exists. A single proton, a single electron, and yet from this modest beginning, almost everything is built. The stars are mostly hydrogen. The vast clouds drifting between galaxies are mostly hydrogen. Even the water in every living cell carries hydrogen at its core. It is the universe's most faithful material, woven through all of creation, like a quiet thread holding the whole tapestry together. The Big Bang Theory does not merely describe the universe in broad strokes. It predicts with remarkable precision the exact ratio of hydrogen to helium we observe today, roughly 3/4 hydrogen and 1/4 helium, with only trace amounts of anything heavier. Scientists calculated this ratio from the known physics of the early universe, and when they looked out at the cosmos, the numbers matched. That agreement between prediction and observation is one of the most reassuring foundations the theory rests upon. In the first few minutes after the Big Bang, the universe was a furnace of almost incomprehensible energy, and within that radiant heat, the lightest elements were forged. Protons and neutrons fused together, building hydrogen, helium, and tiny traces of lithium. This process is called Big Bang nucleosynthesis, and it lasted only a matter of minutes before the universe cooled enough for it to cease. In those brief blazing moments, the raw ingredients of every star and every world were quietly assembled. For the first 380,000 years of its existence, the universe was so dense and so hot that light could not travel freely through it. Photons were constantly scattered by a thick plasma of charged particles, the way sunlight scatters inside a cloud. The universe was opaque, a warm, luminous fog with no clear view in any direction. Everything that happened in those early hundreds of thousands of years is hidden from our telescopes, sealed behind a glowing curtain we cannot see through. Then, about 380,000 years after the Big Bang, the universe had cooled enough for electrons to settle into orbit around atomic nuclei. In a relatively brief period, the fog cleared. Photons were suddenly free to travel unimpeded across space, and they have been traveling ever since. That ancient release of light, called recombination, is what we detect today as the cosmic microwave background. Every time a radio telescope maps that faint glow, it is reading a message written before a single star had ever formed. The cosmic microwave background is not perfectly uniform. Scattered across its ancient surface are tiny temperature variations, fluctuations so small they amount to differences of only about 1 part in 100,000. Yet these faint ripples were the seeds of everything. Regions that were ever so slightly denser than their surroundings had a little more gravitational pull, and over vast stretches of time, that pull gathered more and more matter around them. All the structure we see in the universe today grew from those whisper-thin variations in the earliest light. Gravity is patient. Over hundreds of millions of years, it steadily drew matter toward the slightly denser regions seated in that ancient light. Thin wisps of gas grew into clouds. Clouds collapsed into the first stars, and stars gathered into the first galaxies. Those galaxies in turn were drawn toward one another, forming clusters and vast filaments stretching across the cosmos. All of this immense architecture, every galaxy that has ever existed, grew from variations smaller than the finest tremor in still water. Ordinary matter, the atoms that make up stars, planets, and everything we can touch or see, accounts for only a small portion of what fills the universe. About 27% of the universe's total energy content is something scientists call dark matter. It does not emit, absorb, or reflect light, so it remains invisible to every telescope ever built. Yet its gravitational influence is unmistakable. Without dark matter, galaxies would not hold together, and the large-scale structure of the cosmos could never have formed the way we observe it. If dark matter is the universe's hidden scaffolding, dark energy is its quiet and relentless breath. Making up about 68% of the universe's total energy content, dark energy is the name scientists give to whatever is driving the accelerating expansion of space. It does not clump, it does not fade, and it fills every corner of the cosmos with a kind of outward pressure that grows more dominant as the universe ages. Its true nature remains one of the most serene and profound mysteries in all of science, a vast, invisible presence woven into the fabric of everything. Ordinary matter accounts for only about 5% of the universe. Everything we have ever seen, touched or measured, every star, every ocean, every grain of sand, every living thing, makes up just 5% of all that exists. The remaining 95% is composed of dark matter and dark energy, things we cannot directly observe or hold. It is a humbling and somehow comforting thought. The visible world, for all its richness, is only a thin, luminous layer resting atop something far vaster and far quieter. Let yourself settle a little more deeply now. There is nowhere you need to be, nothing you need to hold on to. Feel the weight of your body resting, fully supported. Let your shoulders drop, let your jaw soften, let your hands open gently. Each breath arrives on its own, slow and easy. You do not need to think about any of this. You can simply let the words wash over you like a slow tide, carrying you quietly toward sleep. Everything is still. Everything is well. The universe's expansion has been accelerating since about 5 billion years ago. For most of cosmic history, gravity had been gradually slowing the outward rush of space, but roughly 5 billion years ago, something shifted. A kind of outward pressure, which scientists call dark energy, began to overtake gravity's pull. Since then, the universe has been expanding faster and faster, with distant galaxies receding from us at ever-increasing speeds. That turning point happened long before our solar system even formed, woven quietly into the fabric of space itself. Albert Einstein's general theory of relativity describes the large-scale geometry of spacetime, published in 1915. It replaced the older idea of gravity as a simple force with something far more elegant, the idea that mass and energy curve the very fabric of space and time, and that this curvature is what we experience as gravity. Planets orbit stars not because they are pulled by an invisible string, but because they follow the natural contours of curved spacetime. It is a picture of the cosmos as something supple and alive, shaped by everything within it. General relativity predicts that spacetime itself can expand or contract. Einstein's equations do not describe a fixed, unchanging stage on which events play out. They describe a dynamic geometry, one that can stretch, curve, and flow. Space itself is not merely a container for matter, it is a participant in the story of the cosmos. The same equations that describe a planet curving through space also describe the entire universe, swelling outward across billions of years. The universe is not expanding through space, it is space itself that expands. In 1922, a Russian mathematician named Alexander Friedmann derived solutions to Einstein's equations that described a universe in motion. Einstein himself had assumed the universe must be static and had added a special term to his equations to keep it that way. Friedmann set that term aside and followed the mathematics wherever it led, and it led him to a universe that was either expanding or contracting. His work was largely overlooked at the time, but it laid the quiet mathematical foundation for everything that came after. The equations had known the answer before anyone was ready to hear it. In 1927, a Belgian priest and physicist named Georges Lemaitre independently arrived at the same conclusion: the universe was expanding. Working from his own careful reading of Einstein's equations and from early observations of distant galaxies, Lemaitre proposed that space itself was growing. He even estimated a value for the rate of that expansion, a discovery that would later be credited to Edwin Hubble, whose observations followed 2 years later. Lemaitre's insight came from a quiet blending of deep mathematics and careful observation, a mind at rest with both science and wonder. Lemaitre called the origin point of the universe the primeval atom. He imagined that all the matter and energy of the cosmos had once been compressed into a single, unimaginably dense particle, something like an atom, but containing everything. From this primeval atom, the universe had burst outward and continued to expand and evolve over vast stretches of time. The image is simple and almost tender. The entire cosmos, all its galaxies and light and silence, folded into one infinitely small beginning. It is a thought that can rest in the mind, like a smooth stone held gently in the hand. In the 1960s, Roger Penrose and Stephen Hawking proved a set of mathematical results known as the singularity theorems. Working with the framework of general relativity, they showed that under very broad and reasonable conditions, any universe like ours must have begun at a singularity, a point where density and curvature become infinite and the equations of physics cease to give meaningful answers. It was a landmark achievement, both elegant and sobering. The mathematics itself was pointing to a boundary, a place where the familiar rules of the cosmos quietly ran out. The singularity theorems reveal that general relativity breaks down at the moment of the Big Bang. The same equations that so beautifully describe the large-scale universe, the curving of spacetime around galaxies, the expansion of space across billions of years, simply stop working when traced all the way back to that first instant, at the singularity. Densities and temperatures become infinite, and the theory can no longer tell us what was happening. It is not a failure of imagination, but a signpost. The universe at its very beginning requires a deeper understanding than any single theory has yet provided. And that deeper understanding is where our quiet journey is only just beginning. Classical physics cannot describe the conditions that existed at the Planck scale. The familiar laws, Newton's mechanics, Einstein's relativity, even the elegant equations of thermodynamics were built to describe a universe that already exists, already has space and time and matter arranged in recognizable ways. But at the very threshold of the Big Bang, where temperatures and densities soar beyond all ordinary measure, those laws reach the edge of their domain. They do not break violently. They simply fall silent, the way a language runs out of words for something it has never needed to name. The Planck time is approximately 5.39 times 10 to the minus 44 seconds, written out. That is a decimal point followed by 43 zeros, and then the digits 539. It is the smallest meaningful unit of time that current physics can speak about. Before this interval has passed after the very beginning, our best theories cannot tell us what was happening. It is not that time was moving differently. It is that the concept of time itself may not have had the meaning we give it now. The universe was doing something, but we have not yet found the language to describe it. Let your body settle a little more deeply into wherever you are resting. There is nothing you need to hold on to right now. Let your shoulders release. Let your jaw soften. Let your hands lie open and easy. Each breath is slower than the last, each exhale carrying a little more of the day away. You are simply here, drifting at the edge of something vast and unhurried, and that is exactly where you are meant to be. There is nothing to figure out, nothing to remember. Just the quiet and the slow, easy rhythm of your own breathing. The Planck length is approximately 1.616 times 10 to the minus 35 meters. To feel the scale of this, consider that a single proton is already almost unimaginably small, and the Planck length is roughly 100 million billion times smaller than that. It is the distance below which the smooth, continuous fabric of space, as we understand it, loses its meaning entirely. Physicists believe that at this scale, space itself may be grainy or foamy, or woven from something we do not yet have a name for. It is the finest possible stitch in the fabric of existence. At energies above the Planck scale, quantum effects dominate everything. In the ordinary world, quantum mechanics governs the very small and gravity governs the very large, and the two rarely need to speak to each other. But at Planck energies, the two realms converge completely. Gravity becomes as strong as the other fundamental forces, and the smooth, curving spacetime of general relativity is torn apart by quantum uncertainty. The universe at that moment was not a place of stillness. It was a place where the very structure of space and time trembled and shifted with every possible configuration at once. A complete theory of quantum gravity does not yet exist. This is one of the most profound open questions in all of science: how to reconcile the two great pillars of modern physics, general relativity and quantum mechanics, into a single coherent framework. Each theory is extraordinarily successful in its own domain. Each has been tested and confirmed in hundreds of ways, and yet they speak different mathematical languages, rest on different assumptions, and cannot simply be combined. The gap between them is not a failure but an invitation, a wide open space in our understanding, waiting patiently for the right idea. String theory is one of the leading candidate frameworks for a theory of quantum gravity. At its heart, string theory proposes that the fundamental constituents of nature are not point-like particles but tiny, one-dimensional vibrating filament strings. Different vibrational modes of these strings correspond to different particles, and gravity emerges naturally from the mathematics of their interactions. The theory requires extra dimensions of space beyond the three we experience, dimensions that are curled so tightly they remain hidden from ordinary observation. It is an intricate and beautiful structure, like a piece of music whose full harmony can only be heard from very far away. Loop quantum gravity is another approach to the same deep problem. Rather than replacing particles with strings, loop quantum gravity takes the geometry of spacetime itself and quantizes it, breaking it into discrete, finite chunks, the way matter is made of atoms. In this picture, space is woven from a network of interconnected loops, each one carrying a quantum of area. There is no smooth, continuous backdrop for the universe to exist within. Space itself is the network, and at the smallest scales it has a granular, almost crystalline structure. It is a vision of reality that is both radical and oddly intimate, the universe not as an infinite void, but as a vast, intricate lattice. Both string theory and loop quantum gravity remain experimentally unverified. Scientists believe both frameworks contain genuine mathematical insight, and each has produced beautiful and surprising results within its own domain. But neither has yet made a prediction that could be tested and confirmed by an experiment we are currently able to perform. The energies required to probe the Planck scale directly are far beyond anything our instruments can reach. And so these two great frameworks rest in a kind of suspended conversation with the universe, waiting for the moment when observation and theory can finally meet. The patience required is immense, and it is, in its own way, a form of wonder. The concept of cosmic inflation was proposed by the physicist Alan Guth in 1980. Working on a problem in particle physics, Guth realized that a brief period of extraordinarily rapid expansion in the universe's earliest moments could resolve several deep puzzles about why the cosmos looks the way it does today. He proposed that in a tiny fraction of its first second, the universe expanded by an almost incomprehensible factor, far faster than light, driven by a form of energy built into space itself. It was a quiet, almost accidental discovery, a young physicist, late at night, finding that a single elegant idea could explain the shape of everything. The light entering your eyes tonight is, in some sense, the distant echo of that expansion. Inflation posits that in the universe's very first fraction of a second, space expanded at an exponential rate, far beyond anything that has happened since. This was not matter moving through space, but space itself stretching, doubling and doubling again in an almost unimaginably brief interval. The driving force was a form of energy embedded in the fabric of the early cosmos, pushing outward with extraordinary intensity. In the span of time it takes light to cross a single proton, the universe grew from something smaller than an atom to something vast. It is one of the most dramatic events in all of natural history, and yet it unfolded in near-perfect silence. Inflation explains why the cosmic microwave background has almost exactly the same temperature in every direction we look. Without inflation, regions of the sky that appear opposite each other would never have been in contact. They would have had no way to reach the same temperature. But inflation stretched what was once an extraordinarily tiny, well-mixed region into the entire observable universe. Every part of the sky we see today was once in intimate contact, sharing its warmth evenly before being carried apart. The uniformity of that ancient glow is not a coincidence. It is the memory of a moment when everything was one. Inflation also explains why the universe appears spatially flat, why the geometry of space, measured across vast distances, shows no detectable curvature. Before inflation, the universe could have had any shape, curved inward like a sphere, or curved outward like a saddle. But the extraordinary stretching of inflation ironed out whatever curvature existed, the way pulling a small patch of wrinkled fabric smooths it into a taut, featureless plane. The universe we inhabit today is flat to within the precision of our finest measurements. It is a geometry of quiet equilibrium, balanced, open, and without edge. There is nothing you need to hold onto right now. No thought requires your attention. No question needs an answer tonight. Let your body settle a little more deeply into the surface beneath you, and let your breath move slowly, without effort. Each exhale carries something away, a small weight, a small tension, and each inhale brings only stillness. The universe is vast and unhurried, and you are resting within it. There is nowhere to be, nothing to solve. Just this breath, and then the next, and the quiet dark all around you. Inflation also resolves a curious puzzle about particles called magnetic monopoles. Grand unified theories, frameworks that attempt to merge the fundamental forces of nature, predict that the early universe should have produced vast numbers of these exotic particles, each carrying a single magnetic pole. Yet none have ever been detected. Inflation offers an elegant resolution. The exponential expansion diluted the density of monopoles so thoroughly that the chance of finding even one within the entire observable universe becomes extraordinarily small. They were not destroyed. They were simply spread so far apart that the cosmos, to us, appears to contain none at all. During inflation, the universe was not entirely smooth. Quantum mechanics ensures that even in the most featureless stretch of space, tiny fluctuations arise, whisper-thin variations in energy density, smaller than anything that can be directly observed. Inflation took these infinitesimal quantum tremors and stretched them to cosmic scales, imprinting them across the fabric of the expanding universe. These microscopic wrinkles became the seeds from which everything grew: galaxies, clusters of galaxies, the great filaments and voids of the cosmic web. Every star you have ever seen traces its origin to a quantum shiver that occurred in the universe's first sliver of a second. Inflation predicts that the pattern of those primordial fluctuations should be nearly scale invariant, meaning that the density variations are roughly the same strength across all sizes, from the very small to the very large. This is a precise, testable prediction. The seeds of cosmic structure should not favor any particular scale, but should be distributed with a nearly even hand. It is an elegant and specific claim, the kind that separates a genuine scientific theory from a mere story. The mathematics of inflation, developed in the years after Alan Guthr's original proposal, converged on this prediction from multiple directions, each arriving at the same quiet answer. The Planck satellite, a European Space Agency mission that mapped the cosmic microwave background with extraordinary precision, confirmed that the spectrum of primordial perturbations is indeed nearly scale invariant. Launched in 2009 and completing its observations in 2013, Planck measured the temperature fluctuations of the ancient light with a delicacy that had never before been achieved. The pattern it found matched the inflationary prediction with remarkable fidelity. It was a moment of deep satisfaction for cosmology, a theory born from abstract mathematics, confirmed by light that had been traveling toward us for nearly 14 billion years. Inflation could not continue forever. The energy driving that extraordinary expansion was stored in a field, a smooth, slowly evolving quantum field that physicists call the inflaton. For inflation to end, this field had to release its energy in a controlled way, transitioning from its high energy state to a lower one. This process is called reheating, and it marks the moment when the cold, nearly empty universe produced by inflation was transformed into the hot, dense fireball that we more traditionally associate with the Big Bang. Reheating was not an explosion in the ordinary sense. It was more like a long, slow exhale, energy dispersing outward, filling the universe with warmth. During reheating, the energy of the inflaton field was converted into the ordinary particles that would go on to form everything we know. The inflaton oscillated around the lowest point of its energy landscape, and as it did, it decayed, transferring its energy into a dense hot plasma of quarks, electrons, photons, and the other fundamental constituents of matter. From that plasma, in the minutes and years that followed, came hydrogen and helium, then stars, then heavier elements, then planets, then life. The connection from that ancient field to the world around you tonight is unbroken. The warmth of your own body carries, at its deepest root, the last echo of inflation's long surrender. The force that drove inflation is thought to arise from a hypothetical scalar field, a smooth, pervasive field that physicists call the inflaton field. A scalar field is one that has a single value at every point in space, like a vast invisible ocean of energy spread evenly across the cosmos. The inflaton field is not a particle you could hold or a force you could feel. It is a deeper layer of reality, a kind of quiet tension woven into the fabric of the very early universe, gently and then not so gently, pushing space itself apart. Despite its central role in our best understanding of the early universe, the true identity of the inflaton field remains unknown. Physicists do not know what kind of particle corresponds to it, what its precise energy was, or how it fit into the broader family of known forces and fields. It is, in a sense, a placeholder, a beautifully useful mathematical shape that does exactly what inflation requires, yet whose deeper nature remains just beyond our reach. Scientists continue to search, with quiet patience, for clues that might one day reveal what the inflaton truly was. The entire epoch of inflation is thought to have lasted an almost incomprehensibly brief span of time, from roughly 1/1,000,000,000 of a trillionth of a trillionth of a second after the beginning, to about 100 trillion trillionths of a second. These are durations so small that no clock, no instrument, no human intuition can truly hold them. And yet within that vanishing sliver of time, the universe was remade entirely. The whole arc of cosmic history, every galaxy, every star, every quiet night like this one, was shaped in those fleeting, wordless moments. During inflation, the universe expanded by a factor of at least 10 to the 26, that is, 1 followed by 26 zeros. A region smaller than a single proton was stretched to a scale larger than a present-day galaxy, all within that brief, extraordinary interval. The expansion was not movement through space. Space itself was growing, smoothly and in every direction at once. It is one of the most staggering transformations in the history of anything, and yet it happened in perfect, featureless silence, with no sound, no light, no witness. There is nothing you need to hold on to right now. Let the weight of the day dissolve, the way a breath dissolves into the open air. Allow your shoulders to soften, your hands to rest open and still. You have traveled far today, through hours and thoughts and small efforts, and now all of that can simply be set down. Let your body grow heavy and warm. Let your breathing find its own slow, natural rhythm. There is nowhere to go, nothing to figure out. Just this quiet and the gentle dark and the deep rest that is already waiting for you. Many versions of inflationary theory carry within them a remarkable and somewhat surprising implication. Once inflation begins, it never truly stops everywhere at once. This is called eternal inflation. In most regions, inflation eventually ends, as it did in the part of the universe we inhabit. But in other regions, quantum effects keep the inflaton field from settling down, and inflation continues, stretching space ever further outward. The universe in this picture is not a single finished thing, but an ever-growing, ever-branching expanse, quietly generating new space in the regions beyond any horizon we could ever see. The mechanism behind eternal inflation is rooted in the quantum nature of the inflaton field. Quantum fields are never perfectly still. They ripple and fluctuate, even in their lowest states. In some regions of space, these fluctuations nudge the inflaton field upward in energy, rather than allowing it to roll down toward its resting point. In those regions, inflation reignites and continues. The result is that inflation, once started, tends to sustain itself across the broader cosmos, even as individual pockets settle down and give rise to regions like our own, warm, structured, and full of stars. Each region where inflation ends becomes, in effect, its own separate universe, a bubble of settled space, expanding at its own pace, enclosed within a broader sea of still inflating space. These bubble universes are so widely separated that no signal, no light, no information could ever pass between them. They are profoundly, permanently beyond one another's reach. Scientists sometimes picture them as bubbles rising through an endless, effervescent ocean, each one complete in itself, unaware of the others, drifting in its own quiet corner of an incomprehensibly larger whole. Within each bubble universe, The laws of physics may not be the same as our own. The inflaton field can settle into different energy states in different bubbles, and those different states can give rise to different values for fundamental constants: the strength of gravity, the mass of the electron, the rate at which atoms form and stars ignite. In some bubbles, the conditions may be too extreme for any structure to persist. In others, something like chemistry, and eventually something like life, might quietly arise. Our universe, with its particular and finely balanced constants, is simply the bubble in which we find ourselves. The vast collection of all these bubble universes, each born from the endless churning of eternal inflation, is given a single name: the multiverse. It is a word that carries enormous weight, the idea that our universe, immense and ancient as it is, may be only one among an uncountable multitude. Each member of the multiverse is its own complete cosmos, with its own history, its own constants, its own long silence before any stars were born. The multiverse is not a place you could travel to. It is more like a quiet understanding that what we can see is only the smallest, most intimate part of what exists. The multiverse hypothesis, for all its grandeur, remains beyond the reach of direct experimental testing with our current methods. A theory that cannot be tested is not wrong. It is simply waiting. Scientists hold it carefully, the way you might hold a thought that feels true but cannot yet be confirmed. The mathematics is coherent, the reasoning is sound, and yet the multiverse remains, for now, a beautiful and well-reasoned idea suspended just beyond the edge of what we can measure or touch. In 1983, the physicist André Linde developed a variation of inflation known as chaotic inflation. Rather than requiring the universe to begin in a very specific, finely arranged state, Linde's model allowed inflation to start from almost any initial condition, including deeply disordered, chaotic ones. The inflaton field could begin at a high energy value almost anywhere, and from that starting point, the familiar process of expansion would unfold. It was a more forgiving picture of origins, one that did not demand perfection at the very first moment. Chaotic inflation carries within it a remarkable implication. Our universe may have begun from a single quantum fluctuation. In the language of quantum mechanics, empty space is never truly empty. It hums with possibility, with tiny, momentary variations in energy. Linde's model suggests that one such fluctuation, occurring in a region of sufficiently high energy, could have been enough to seed the entire process. The whole vast architecture of stars and galaxies and deep cosmic time may have grown from something no larger than a tremor in the fabric of what existed before. A year before Linde's chaotic model, in 1982, the physicist Alexander Vilenkin proposed something even more striking: that the universe may have tunneled into existence from nothing. Quantum tunneling is a well-established phenomenon. Particles can pass through barriers that classical physics says they cannot cross. Vilenkin extended this idea to the cosmos itself, suggesting that the universe as a whole made a kind of quantum leap, crossing from a state of absolute nothingness into the first moment of existence. It is one of the most quietly astonishing ideas in all of science. In Vilenkin's framework, the word nothing is given a very precise meaning. It is not empty space, nor a dark void waiting to be filled. It is a quantum state with no space, no time, and no matter whatsoever, a condition so complete in its absence that our ordinary intuitions simply have no foothold. And yet, in quantum theory, even such a state carries the possibility of transition. The universe in this picture did not arise from something that existed before. It arose from a quantum state in which the very concepts of before and after had not yet come to be. Let your body grow still now. There is nothing you need to hold on to, nothing you need to figure out. Let your shoulders settle, let your hands rest open and easy. With each slow breath, the thoughts of the day grow a little more distant, like lights on a far shore, dimming gently as you drift. You are safe, you are warm, and the only thing asked of you right now is to let go. Let the breath come and go on its own. Let the mind soften. You are drifting quietly toward sleep. In 1983, the physicists James Hartle and Stephen Hawking put forward what they called the no-boundary proposal, one of the most elegant and far-reaching ideas ever offered about the origin of the universe. Working together, they applied the mathematics of quantum mechanics to the geometry of spacetime itself, asking what the universe would look like if it had no edge, no wall, no hard beginning. Their answer was a universe that is complete and self-contained, one that simply is, without needing anything outside itself to explain how it started. At the heart of the no-boundary proposal is a remarkable reframing of what time actually is near the Big Bang. In our everyday experience, time and space are clearly different things. One flows, the other extends. But in the Hartle-Hawking model, very close to the origin of the universe, time behaves more like a dimension of space. It does not flow forward from a fixed starting point, it curves and blends into the spatial dimensions around it. The distinction between time and space dissolves. The way the surface of a sphere has no single point you could call the beginning. Hawking himself offered a wonderfully disarming way to understand what the no-boundary proposal means for the question of what came before the Big Bang. Asking what existed before the Big Bang, he suggested, is a little like asking what lies south of the South Pole. The South Pole is a real place, a well-defined point on the surface of the Earth, and yet the question of what is south of it simply has no answer. Not because we lack information, but because the question does not correspond to anything real. In the same way, before the Big Bang may not be a time that is hidden from us, it may simply be a direction that does not exist. The no-boundary proposal is expressed mathematically through what is called the no-boundary wave function. In quantum mechanics, a wave function describes the range of possible states a system might be found in, weighted by their probability. Hartle and Hawking extended this idea to the entire universe. Their wave function assigns a probability to each possible history the cosmos might have. Some histories are smooth and gradual, others are more turbulent. The universe we observe, with its particular shape and structure, is simply one history among many, one of the more probable ones, quietly selected from an immense range of possibilities. Neil Turok and Stephen Hawking later returned to the no-boundary proposal together, revising and debating its foundations in ways that deepened our understanding of what it truly implied. Their collaboration was not always one of smooth agreement. Turok raised careful, probing questions about whether the original formulation actually predicted a universe like ours. Through that exchange, the proposal was tested, refined, and made more precise. Even between two of the most gifted minds in theoretical physics, the greatest ideas are not fixed monuments but living things, slowly shaped by patient, unhurried inquiry. One of the most quietly beautiful consequences of the no-boundary proposal is that it predicts a universe with a smooth, gradual beginning, no singularity, no infinitely dense point where all equations collapse. Instead of a hard, violent edge, the origin of the universe in this model is more like the rounded tip of an egg, curved, continuous, and complete. There is no moment of infinite density to trouble the mathematics, no wall of unknowing where physics simply stops. The universe in this picture begins as gently as a thought forming in stillness. The mathematician and physicist Roger Penrose, one of the most original thinkers in modern science, proposed a deeply different vision of the cosmos, a model he called conformal cyclic cosmology. Penrose had spent decades thinking about the geometry of spacetime, about the nature of singularities, and about the profound puzzle of why the universe began in such an orderly low-entropy state. His answer was not to look for what came before the Big Bang in the usual sense, but to suggest that the very concept of before and after might be far more circular and far more beautiful than we had imagined. In conformal cyclic cosmology, the universe does not simply begin once and expand forever. Instead, it passes through an endless succession of great cycles, each one called an aeon. The word aeon itself carries a sense of almost unimaginable duration, and in Penrose's model, each aeon is itself a complete universe, vast beyond measure, unfolding across billions upon billions of years. There is no final end and no absolute beginning. The cosmos breathes in and out across an infinite series of these great epochs, each one a universe entire unto itself, and yet connected to what came before and what will follow. Each aeon in Penrose's model follows a familiar arc. It begins with a Big Bang, a hot, dense, radiant birth, and then expands outward across immense spans of time, gradually cooling and thinning. Stars form and burn and fade. Galaxies drift apart. Eventually, the last black holes evaporate, and the universe stretches into a vast, cool, nearly featureless expanse, expanding ever faster under the influence of dark energy. This final accelerating expansion is not a tragedy in Penrose's vision. It is a preparation, a transition, a quiet drawing of breath before something new begins. Here is where Penrose's model arrives at its most extraordinary and restful insight: the very remote future of one aeon. That vast, cold, nearly empty expanse becomes, through a precise mathematical transformation, the fiery beginning of the next. The mathematics of conformal geometry, which describes shapes and angles without reference to scale, allows an infinitely expanded universe to be mapped smoothly onto the tiny, dense beginning of a new one. What looks like an ending from inside one aeon is, from another vantage, a birth. The last whisper of one cosmos becomes the first breath of another, and the cycle continues without interruption. Let your body settle a little more deeply now into wherever you are resting. There is nothing left to hold. Let your shoulders soften. Let your hands open. Let the weight of the day dissolve away from you. Your breath is slow and even. Each exhale carries a little more tension out of you, and each inhale brings only stillness. You do not need to follow every thought or remember every word. Simply rest here in the warmth and the quiet, and let yourself drift a little further toward sleep. You are safe, you are still, and there is nothing at all that needs your attention right now. Penrose has gone further than pure theory, suggesting that his model leaves a faint, observable mark on the oldest light we can detect. He and his colleagues examined the cosmic microwave background radiation and reported finding patterns of concentric rings, subtle variations in temperature arranged in circular formations across the sky. These rings, he proposed, are echoes of the final moments of the previous aeon, imprinted on the fabric of our own universe's beginning. The thought is quietly astonishing that the oldest light in our cosmos might carry within it the faint memory of an entire universe that came before. The scientific community has received Penrose's ring evidence with careful, measured skepticism. Several independent research teams have examined the same cosmic microwave background data and reached different conclusions, finding that the patterns Penrose identified could arise naturally from the known statistical properties of the background radiation itself, without requiring any signal from a prior aeon. This is how science works at its most careful and honest. An idea is offered with sincerity, the evidence is examined by many eyes, and the verdict, for now, remains open. The rings are neither confirmed nor dismissed. They rest, unresolved, in the quiet archive of things we do not yet fully know. In the year 2001, the physicists Paul Steinhardt and Neil Turok introduced a strikingly different vision of cosmic origins, one they called the ekpyrotic model. The name comes from the ancient Greek word for conflagration, a great fire, though the mood of the model itself is less about burning than about collision. about two vast surfaces meeting in a moment that we experience as the beginning of everything. Steinhardt and Turok drew on the mathematics of string theory to construct a universe not born from nothing, but born from contact, from the slow, inevitable meeting of two immense structures drifting through a higher dimensional space. The ekpyrotic model draws its deepest inspiration from string theory's proposal that the universe has more dimensions than the three we can see and move through. String theory suggests that beyond the familiar dimensions of length, width, and height, there are additional spatial dimensions curled and folded at scales far too small for any instrument to directly measure. The ekpyrotic model reaches into this richer geometry and borrows its architecture, using those hidden dimensions as the very stage upon which the story of cosmic origins unfolds. In the ekpyrotic picture, our entire universe, every galaxy, every star, every quiet corner of space, exists on an immense paper-thin surface called a brane, short for membrane. Imagine the whole of everything you can see or touch resting on a single vast sheet, like the surface of a still lake that extends without end in every direction. We live on this brane without any awareness of the deeper space surrounding it, the way a ripple on water has no knowledge of the air above or the depths below. At the heart of the ekpyrotic model lies a profound and strangely serene idea. The event we call the Big Bang was not a creation from nothing, but the moment when two of these immense branes drifted slowly together and touched. The collision released an enormous surge of energy across the entire surface of our brane, filling it with heat and light and the raw material of everything that would follow. What we experience as a beginning was, in this telling, simply a meeting, vast, slow, and inevitable, like two great tides finally finding each other across an unimaginable distance. These branes do not float in ordinary space. They exist within a higher dimensional realm that physicists call the bulk, a deeper space that contains our brane and others, the way a great ocean contains the surfaces of waves. Bulk is not something we can visit or observe directly. It lies beyond the reach of light or any signal we know how to send. Yet, in the mathematics of string theory, it is as real as anything else, a vast and featureless expanse through which our universe drifts like a leaf, resting on the surface of an invisible sea. Steinhardt and Turok extended their model further, imagining that the collision between branes was not a single, unrepeatable event, but one beat in an endless, unhurried rhythm. In the cyclic ekpyrotic model, branes drift apart after each collision, then slowly, over immense stretches of time, fall toward each other again. Each meeting produces a new universe, a new expansion, a new era of stars and galaxies. The cosmos, in this vision, does not begin or end. It breathes, slowly and without urgency, across durations that make even a billion years feel like the pause between one heartbeat and the next. One of the most quietly elegant features of the ekpyrotic model is the way it sidesteps the singularity, that point of infinite density and temperature where the equations of general relativity break down and cease to offer any answers. Rather than compressing all of existence into a dimensionless point, the ekpyrotic model replaces that moment with a brane collision, a finite, extended event spread across an enormous surface. The infinite is gently dissolved, replaced by something finite and physical. It is a graceful resolution, like finding that what seemed an impassable wall was always, in fact, a door. A separate and equally thoughtful approach to the question of cosmic origins comes from a field called loop quantum cosmology, which takes the framework of loop quantum gravity and applies it not just to small regions of space, but to the entire universe at once. Loop quantum gravity is an attempt to describe space-time itself as a quantum structure woven from discrete, indivisible units rather than flowing as a smooth continuum. When that idea is extended to the whole cosmos, The result is a picture of the universe's earliest moments that looks strikingly different from the classical story of the Big Bang. Let your breath slow a little more now, and let your thoughts grow lighter. There is no need to hold on to anything, not the ideas, not the images, not even the words. Simply let them pass through you, like a breeze moving through tall grass, there for a moment and then gone. Your body is heavy and warm. Your mind is growing softer at its edges. There is only this moment, this stillness, this quiet invitation to rest. Let yourself drift a little further now, without effort, without direction, toward the deep and welcoming ease of sleep. Within loop quantum cosmology, space is not an infinitely divisible smoothness. Instead, it is composed of discrete, irreducible units, the smallest possible chunks of space that cannot be divided any further. These fundamental grains of space are woven together into the fabric of reality, the way individual threads are woven into cloth. At the scales of ordinary experience, this granularity is entirely invisible, and space feels perfectly smooth and continuous. But at the deepest level, at the very foundation of existence, space has a texture, a fineness, a structure, an irreducible smallness that sets a natural lower limit on how compressed the universe can ever become. Because space in loop quantum cosmology cannot be compressed beyond its fundamental grain size, the crushing contraction that classical physics imagines ending in a singularity instead reaches a point of maximum density and then rebounds. The universe does not collapse to a point and vanish, it bounces. This moment is known as the Big Bounce, and it suggests that what we call the Big Bang was not a beginning but a rebound. The universe before us had been contracting for an immense span of time, and our entire expanding cosmos emerged from the moment that contraction reversed. The thought rests gently in the mind, like the turning of a tide. The Big Bounce replaces the singularity with a quantum bounce from a contracting phase, rather than the universe collapsing to an infinitely dense point and simply ending. Loop quantum cosmology describes a gentler turning, a moment where contraction gives way to expansion, the way a breath held to its limit naturally releases. The singularity, that troubling boundary where the equations of classical physics break down entirely, is dissolved. In its place stands a finite, traversable threshold, a crossing point between one cosmic era and the next. The contracting phase before the bounce may have left imprints on the cosmic microwave background. If a prior universe existed, collapsing slowly across immeasurable spans of time, the structures and patterns within it might have been carried through the bounce and pressed faintly into the fabric of our own cosmos. Scientists believe these imprints, if they exist, would appear as subtle anomalies in the ancient light we call the cosmic microwave background, faint whispers of a world that came before, written in the temperature of the oldest light we can see. No confirmed signatures of a pre-bounce universe have been found in the cosmic microwave background. Scientists have searched carefully through the data, looking for the characteristic patterns that loop quantum cosmology predicts might survive the bounce. So far, the ancient light remains beautifully uniform, yielding no clear evidence of what came before. This absence is not a disappointment, it is simply the honest edge of what we currently know. The universe keeps its deepest secrets with a quiet patience, and the search continues, unhurried and open. String gas cosmology offers an entirely different path, an alternative to inflation rooted in the mathematics of string theory. Rather than invoking a brief period of explosive expansion to explain the universe's large-scale smoothness, string gas cosmology begins from a different set of assumptions about what the very earliest universe was like. It draws on the rich structure of string theory, where the most fundamental constituents of nature are not point-like particles but tiny, vibrating filaments of energy, and it asks what the cosmos would look like if those filaments filled everything from the very start. In string gas cosmology, the universe began as a hot, dense gas of strings. There were no particles as we know them, No atoms, no photons, no familiar building blocks of matter. Instead, the entire primordial universe was a thermal bath of these extended vibrating filaments, winding and oscillating in every direction. Scientists believe this string gas filled a tiny hot space in a state of remarkable equilibrium. It is a vision of beginnings that is both strange and strangely restful, an origin story written not in explosions, but in the slow, warm hum of countless vibrating threads. String gas cosmology proposes that the universe was initially small and static, neither expanding nor contracting. This stands in deliberate contrast to the classical picture of the Big Bang, where the universe begins in furious, rapid change. In the string gas picture, the earliest cosmos rested in a kind of equilibrium, held steady by the interplay of strings winding around the compact dimensions of space and strings vibrating freely within them. This balance kept everything still for a time, the way a scale holds perfectly level when two equal weights rest upon it. In string gas cosmology, extra dimensions of space remain tightly curled and small, while three dimensions gradually expanded to become the vast universe we inhabit. String theory requires more than the three spatial dimensions of ordinary experience, and this model offers a natural explanation for why we only perceive three. The winding strings that wrapped around the extra dimensions prevented those directions from growing, while the three familiar dimensions were free to unfurl. It is a quietly elegant idea that the shape of our universe was determined not by force, but by the geometry of what was wound and what was free. The light entering your eyes tonight has traveled through a cosmos whose very dimensions were once held still by the tension of vibrating strings. The holographic principle suggests that all the information contained within a volume of space is fully encoded on its surrounding boundary surface. It is a profound and disorienting idea that the three-dimensional richness of a region, every particle, every field, every event within it, could be completely described by a two-dimensional surface wrapped around it, the way the entire contents of a room might somehow be captured in the pattern of light falling on its walls. Scientists believe this principle is not merely a mathematical curiosity, but a deep structural feature of how reality is organized at its most fundamental level. Let your body settle a little more deeply now, wherever you are resting. There is nothing left to figure out tonight, no problem to solve, no thought to follow to its end. Simply let the ideas dissolve. The way mist lifts from a still lake in the early morning, quietly and without effort. Feel the weight of your limbs, the warmth of the air around you, the natural rise and fall of your breathing. You are held. You are still. You are already moving toward the deep, unhurried ease of sleep. Let yourself go there now, slowly and completely. The holographic principle emerged from careful study of black hole thermodynamics, the physics of heat, entropy, and information in the extreme gravity of black holes. When scientists examined how black holes store information, they discovered something unexpected. The amount of information a black hole can hold is not determined by its volume, but by the area of its event horizon, the surface boundary from which nothing escapes. This discovery suggested something far broader, that the universe itself might follow the same rule, with the boundary of any region holding all the information of the space within it. Jacob Bekenstein discovered that black holes carry entropy, and that this entropy is proportional to the area of their event horizon, not their volume, but their surface. This was a remarkable and deeply unexpected finding. Before Bekenstein's work in the early 1970s, it was not clear that black holes had any thermodynamic properties at all. He showed that a black hole's surface area could never decrease, mirroring the way entropy in a closed system never decreases. It was a quiet mathematical discovery that would reshape how physicists understood the relationship between gravity, information, and heat. Stephen Hawking showed that black holes are not entirely dark. They slowly radiate energy outward in a process now known as Hawking radiation. By applying quantum mechanics to the region just outside a black hole's event horizon, Hawking found that pairs of particles are constantly flickering into existence near the boundary. Occasionally, one particle falls inward while the other escapes. Over immense stretches of time, this process causes a black hole to very gradually lose mass and grow dimmer. It was a profound unification of quantum theory and gravity, arriving quietly in a 1974 paper that changed theoretical physics forever. Hawking radiation has never been directly observed and may never be with instruments we currently possess. The effect is extraordinarily faint. For a black hole of stellar mass, the radiation would be far colder than the cosmic microwave background that fills all of space, making it impossible to detect against that backdrop. Scientists are confident in the theoretical foundations, but the signal itself remains beyond reach. It is one of those ideas that lives entirely in the language of mathematics, verified not by telescope or detector, but by the internal consistency of the equations, a truth held gently in abstraction. The holographic universe hypothesis proposes that everything we experience as a three-dimensional reality may be a kind of projection, arising from information encoded on a two-dimensional surface far away. Much as the image on a holographic film appears to have depth and volume, while the film itself is flat, our universe, with all its galaxies, distances, and textures, may be fully described by a lower dimensional boundary. Scientists believe this is not simply a metaphor, but a mathematically precise correspondence, supported by work in string theory and quantum gravity. The depth we perceive may be, in some profound sense, woven from the surface of something we cannot see. Some physicists have proposed that the Big Bang itself was the formation of a black hole, not in our universe, but in some larger, higher-dimensional space that existed before. In this picture, a collapsing region of a parent universe reached such extreme density that it crossed a threshold and formed a new event horizon. And within that horizon, an entirely new universe was born. Our Big Bang, in this view, was not a beginning from nothing but a birth inside a boundary, a cosmic interior that expanded into what we now call home. It is a thought that carries its own kind of stillness, that we may have come from somewhere. In this black hole cosmology, our entire universe exists inside a four-dimensional black hole, the event horizon of that black hole, forming the outer boundary of everything we can observe or measure. The universe we inhabit, with its billions of galaxies and its billions of years of history, would be the interior of a structure that, from outside, appears simply as a point of no return in some vaster realm. We would never be able to see past our own horizon to confirm this, just as nothing inside a black hole can signal outward. It is a model that makes the cosmos feel both immense and, in a strange way, when closed, held within something larger. Nikodem Poplawski developed a theoretical model in which every black hole that forms in any universe gives rise to a new universe within it. In his framework, the matter falling through a black hole does not simply compress to a singularity, but instead bounces and expands into a new region of spacetime, sealed off from the parent universe by the event horizon. Each new universe can itself form black holes, which in turn generate further universes, branching outward in an endless nested structure. The cosmos, in this model, is not a single story but a vast, quietly proliferating family, each universe the child of a collapse, each collapse the seed of a beginning. The many worlds interpretation of quantum mechanics, developed by Hugh Everett in the 1950s, implies that parallel universes are not merely a speculation, but a direct consequence of quantum theory taken at face value. In standard quantum mechanics, a measurement causes a system to settle into one outcome from many possibilities. Everett proposed that no settling actually occurs. Instead, all outcomes happen simultaneously, each in its own branching version of reality. The universe does not choose, it multiplies. Scientists who favor this interpretation consider parallel universes as real as the one we inhabit, differing only in the outcomes of events too small to see. In the many worlds interpretation, every quantum event, every particle interaction, every measurement, every moment of chance at the subatomic level causes the universe to branch into separate realities, each containing a different outcome. The branching is continuous and all-encompassing, happening countless times each second across every atom in existence. The version of you reading these words tonight is just one thread in an incomprehensibly vast fabric of branching histories, all equally real, all unfolding in their own directions. There is something strangely restful in that thought that every possibility is honored somewhere, that nothing is truly lost, only redirected into another quiet current of the whole. Let your thoughts slow now, like water finding its level. There is no need to hold any of these ideas. Let them drift, let them go. Feel the surface beneath you, steady and still. Notice the natural rhythm of your breathing, easy and unhurried, moving all on its own. With each breath out, let a little more of the day release. Your body knows how to rest. Your mind is already growing quieter. You are somewhere warm and safe, and the vast, unhurried universe is continuing all around you, needing nothing from you tonight. Simply let go, gently and completely, and allow sleep to come in its own time. The landscape of string theory predicts roughly 10 to the 500 possible vacuum states, a number so vast it exceeds any quantity in ordinary physics. Each of these states represents a different way the extra dimensions of string theory can curl and fold, producing a different set of physical laws. The number itself is almost impossible to hold in the mind, and yet string theorists accept it as a natural consequence of the mathematics. It is not a problem to be solved so much as a terrain to be understood, immeasurably wide and somehow, quietly, full of order. Each of those vacuum states in the string landscape corresponds to a universe with its own distinct physical constants, its own strength of gravity, its own mass of the electron, its own rate of cosmic expansion. The laws we consider fundamental here, the precise numbers that govern every atom and every star, are simply the values belonging to our particular vacuum. In another region of the landscape, those numbers would be different, and the universe arising there would be shaped by entirely different rules. The physics we know is one dialect in a language with 500 possible alphabets. The anthropic principle offers a quiet answer to the question of why we find ourselves in a universe with the particular laws that permit life. It observes simply that we could only ever find ourselves in a universe capable of producing observers, and so the fact that our universe permits life is not a remarkable coincidence requiring explanation, but a logical consequence of the act of observation itself. We are here asking the question precisely because the conditions allowed us to arise. The universe did not need to be fine-tuned for us. We are simply the portion of it that can look back and wonder. The weak anthropic principle is careful to describe itself not as an explanation, but as a selection effect. It does not claim the universe was designed for us, or that our existence influenced the laws of physics. It simply notes that our observations are filtered through the requirement that we exist to make them. We cannot observe a universe incompatible with our presence, just as a fish cannot observe a dry riverbed. The principle is modest and precise, a reminder that every measurement we make is shaped, at the deepest level, by the fact that someone is there to make it. The strong anthropic principle moves further and more controversially, claiming that the universe is in some sense compelled to produce observers, that consciousness or observation is not an accident of cosmic history, but a necessary feature of any complete universe. This idea sits at the edge of what most scientists consider testable, and many physicists regard it with careful skepticism. Yet it has a certain quiet grandeur, the notion that awareness itself is woven into the fabric of what a universe must become. It is a thought that invites reflection rather than conclusion, and rests most comfortably in the unhurried space between science and philosophy. Time itself, some physicists now suggest, may not have existed before the universe began. It may have emerged gradually from a deeper, timeless quantum state, the way temperature emerges from the collective motion of countless particles, none of which individually possesses warmth. In this view, asking what happened before time is like asking what is colder than absolute zero. The question assumes a framework that does not yet apply. Time, rather than being the stage on which the universe performs, may be one of the universe's own creations, born alongside space and matter from something that had no before at all. The physicist Julian Barber has spent decades arguing that time is not a fundamental feature of reality, but an illusion, a story the mind constructs from a collection of static, timeless configurations he calls nows. In his framework, the universe does not move through time. It simply exists as an enormous landscape of possible arrangements, and what we experience as the flow of moments is the mind threading a path through that landscape. There is no river of time carrying us forward. There is only the stillness of all possible instants and the quiet narrative we weave among them. The thought lands softly, like setting down something heavy you did not realize you were carrying. In some approaches to quantum gravity, the entire universe is described by a single mathematical expression known as the Wheeler-DeWitt equation. Developed in the 1960s by John Wheeler and Bryce DeWitt, this equation attempts to apply quantum mechanics to the universe as a whole rather than to individual particles within it. It is an extraordinary ambition to write down one expression that contains, in principle, all of cosmic history. The equation treats the universe as a quantum system described by a wave function, a probability cloud of all possible shapes and configurations that space-time might take. What makes the Wheeler-DeWitt equation deeply strange and deeply fascinating is that it contains no time variable. In ordinary physics, equations describe how things change over time. Time is always present as the dimension along which everything evolves. But in the Wheeler-DeWitt equation, time simply does not appear. The universe described at this fundamental level is a static object. The wave function does not evolve, it simply is. The flowing, ticking, ever-moving sense of time that fills every waking moment may be, at the deepest level of physical law, entirely absent from the universe's own self-description. The problem of time in quantum gravity is considered by many physicists to be one of the most profound and unresolved puzzles in all of science. On one side, general relativity treats time as a flexible, dynamic dimension woven into the fabric of spacetime. On the other, quantum mechanics requires time as a fixed background against which systems evolve. When the two theories are brought together, time becomes contradictory, present in one framework, absent in the other. Reconciling these two descriptions is not merely a technical challenge. It reaches into the nature of existence itself. And so the question rests, open and unhurried, like a sky too wide to cross in a single night. Let yourself settle a little deeper now. There is nothing to hold on to, nothing to figure out. Let the breath slow on its own, easy and natural. Feel the weight of your body, heavy and still, resting completely. Each thought that drifts through is welcome to pass by, like a cloud moving across a wide, unhurried sky. You do not need to follow any of them. Just rest here, softly, in the warmth of this quiet moment. Some theorists propose that time had no beginning, because it did not arrive all at once. It emerged gradually, condensing out of a deeper quantum substrate, the way morning mist thickens into something visible. In this view, there was never a sharp edge where time started, no precise moment before which nothing existed. Time simply became more and more defined as conditions allowed, the way a melody becomes recognizable only after enough notes have sounded. The absence of a beginning is not emptiness, it is the gentleness of gradual arrival. Quantum foam describes the condition of spacetime at the smallest imaginable scales, the Planck scale, where the fabric of reality is not smooth and continuous, but seething with tiny, ceaseless fluctuations. At this scale, space and time are thought to bubble and froth like the surface of a sea at the microscopic level, constantly flickering in and out of different geometries. It is nothing like the calm, ordered spacetime we experience in daily life. And yet this turbulent, foaming substrate may be the very ground from which all structure and all stillness ultimately rises. The physicist John Wheeler gave this idea its name, quantum foam, in the 1950s, as part of his lifelong effort to understand the deepest nature of space and time. Wheeler was a remarkable thinker, someone who spent decades asking the largest questions physics could hold, and who mentored generations of scientists who carried those questions forward. The term he chose is beautifully humble. Not quantum architecture, not quantum foundation, but foam, something light, transient, and full of air. It is a name that carries within it a sense of wonder without weight. Stephen Hawking introduced the concept of imaginary time as a mathematical tool to sidestep the problem of the singularity at the beginning of the universe. In ordinary mathematics, time is treated as a real number, something that can be measured and counted. But Hawking proposed rotating the time axis in a particular mathematical direction, replacing real time with what mathematicians call imaginary time. This rotation transforms the equations of physics in a subtle but profound way, smoothing out the sharp point of the singularity the way rounding the tip of a cone turns a spike into a curve. Imaginary time is not time as we experience it. It is a mathematical rotation, a reorientation of the time axis, so that it behaves like a dimension of space rather than a dimension of change. In this rotated framework, the equations of physics become more tractable, the singularity dissolves, and the universe can be described as a smooth, closed surface with no edges. It is a technique borrowed from the mathematics of complex numbers, applied with extraordinary elegance to the geometry of the cosmos. The name sounds strange, but the purpose is serene, to find a description of the universe that is whole and unbroken. In the framework of imaginary time, the universe has no boundary and no beginning. Just as the surface of a sphere has no edge, no point where it starts or stops, the universe in imaginary time is a closed, smooth surface with no special starting point. The question of what came before simply loses its footing, like asking what lies south of the southernmost point on Earth. There is no before, not because something is hidden there, but because the geometry itself offers no place for a before to stand. The universe, in this description, is quietly and completely self-contained. A symmetry principle known as CPT symmetry, which links charge, spatial reflection, and time reversal, has led some theorists to a remarkable proposal that the universe before the Big Bang could be a mirror image of our own, running in reverse through time. CPT symmetry is one of the most firmly established principles in particle physics, holding that the laws of nature remain unchanged when you simultaneously reverse the charge of every particle, flip spatial directions, and reverse the flow of time. Applied to cosmology, it suggests the Big Bang was not an absolute beginning, but a point of reflection, a still, central moment between two vast, symmetrical halves of a single cosmic whole. In a universe governed by CPT symmetry, our familiar cosmos of matter expanding forward through time would have a twin, an antimatter universe expanding backward into the past, away from the same Big Bang moment. The two universes together would form a single, symmetric whole, balanced around the instant of the Big Bang, the way a reflection balances in still water. Neither twin would be more fundamental than the other. Each would be the mirror of the other's existence, and the Big Bang itself would be the surface of that mirror, not a beginning, but a point of perfect balance. Something about this image feels restful, like the universe breathing out from a still center. This elegant symmetric model was developed by the physicist Latham Boyle and his colleagues and presented to the scientific community in 2018. What makes it particularly striking is its economy. It does not require exotic new particles, hidden dimensions, or physics beyond what is already known. It works entirely within the framework of the standard model of particle physics, the well-tested foundation of modern physics, simply extended with this single symmetry applied to the universe as a whole. In the landscape of cosmological proposals, it stands out for its quiet simplicity, a reminder that sometimes the most far-reaching ideas arrive without fanfare. What makes the SEAT model particularly graceful is its restraint. It requires no new physics beyond what is already known and tested. The standard model of particle physics, built over decades of careful experiment, already contains everything this framework needs. No exotic particles, no hidden forces, no undiscovered dimensions are called upon. The universe's twin-sided symmetry emerges naturally from principles already sitting quietly at the heart of modern physics. Sometimes the deepest ideas are the ones that ask for the least. Let your body grow heavier now, sinking gently into whatever surface holds you. There is nothing to figure out, nothing to remember, nothing to carry forward into this moment. Let your breath slow on its own, like a tide finding its natural rhythm. Feel the muscles around your eyes soften, your jaw release, your shoulders settle. You are held. The day is finished, and all that remains is this: the quiet, the stillness, the slow drift toward rest. One of the most enduring principles in all of science is the second law of thermodynamics, which tells us that entropy, the measure of disorder within a system, always increases over time. A warm cup of tea cools into the room. A sand castle dissolves into the beach. Smoke drifts and disperses, never gathering back into a flame. This tendency toward spreading, dissolving, and evening out is not a quirk of particular systems. It is woven into the fabric of how time itself moves forward. The universe we observe began in a state of extraordinarily low entropy, a condition of remarkable, almost implausible orderliness, and this sits as one of the most profound and unresolved mysteries in all of cosmology. If entropy tends always to increase, and if the universe has been spreading and dissolving ever since the Big Bang, then the starting point must have been something breathtakingly structured and smooth. Why the universe began in such an ordered state, rather than a disordered one, is a question that has occupied some of the finest minds in theoretical physics for generations. The physicist Roger Penrose has offered a striking way to appreciate just how improbable our universe's low entropy beginning truly was. He estimates that the probability of the Big Bang occurring in the precise, ordered state it did is roughly 1 in 10 raised to the power of 10 raised to the power of 123, a number so astronomically vast it has no name and no analogy in ordinary experience. When Einstein's experience, written out in full, it would require more digits than there are atoms in the observable universe, and yet here we are. The physicists Sheen Carroll and Jennifer Chen offered a thoughtful response to the mystery of low entropy by proposing that the Big Bang was not a beginning but a fluctuation, a spontaneous departure from a vast high-entropy background called de Sitter space. De Sitter space is a model of the universe dominated by a cosmological constant, expanding gently and endlessly, filled with a kind of irreducible quantum haze. Within this eternal, featureless expanse, Carroll and Chen suggested, pockets of lower entropy can occasionally condense, and one such condensation became everything we know. In Sean Carroll's framework, our universe did not arise from a singular, carefully prepared beginning, but nucleated spontaneously from an otherwise empty and featureless de Sitter space, the way a tiny bubble might form in perfectly still water, rising from nothing apparent into brief, expanding existence. The de Sitter background requires no cause and no prior arrangement. It simply persists, and from time to time, through the deep restlessness of quantum probability, something like a universe emerges. Our entire cosmos, in this picture, is one such quiet emergence from the stillness. A thought experiment known as the Boltzmann brain problem arises when physicists take the idea of universes forming from random fluctuations to its logical extreme, and the conclusion is gently absurd. If a sufficiently vast and eternal universe can occasionally produce a low-entropy fluctuation as large as an entire cosmos, it would far more frequently produce something much smaller, a single isolated mind, floating in the void, complete with false memories of a world that never existed. This thought experiment is a kind of philosophical reductio ad absurdum, a way of showing that some theories, taken seriously, lead somewhere quietly untenable. A Boltzmann brain, as physicists have named this strange hypothetical, is a self-aware observer that comes into being not through the long, patient unfolding of cosmic history, but through a random quantum fluctuation assembled fully formed, with a complete inner world of sensations and memories, from the thermal noise of an otherwise empty universe. The concept was inspired by the 19th century physicist Ludwig Boltzmann, who grappled with similar questions about why the universe has an arrow of time at all. The Boltzmann brain is not a scientific prediction so much as a gentle warning about the limits of certain idea. The Boltzmann brain problem does not belong to any single theory. It surfaces as an unwelcome guest in many models that propose an eternal universe governed by random fluctuations. In such frameworks, the mathematics of probability suggests that isolated, fleeting observers would arise far more often than fully formed universes, making it statistically unlikely that we are what we appear to be. This tension quietly haunts a wide range of eternal cosmological models and reminds physicists that a theory must account not only for how a universe can arise, but for why the universe we find ourselves in is the vast, structured, history-rich kind that it is. The arrow of time. It is the deep asymmetry of the Big Bang's initial conditions, its remarkable orderliness, that gives time its direction, like a river shaped entirely by the slope of the land beneath it. Without that astonishingly low-entropy beginning, nothing about the arrow of time can be explained, and, more intimately, neither can our memories. Memory depends on records, and records depend on the past being more ordered than the present, which is only possible because the universe began in a state of extraordinary arrangement. Every recollection you carry, every impression of yesterday, every sense that time has moved, is ultimately rooted in that single, ancient, improbably tidy origin. The whole fabric of remembered experience rests quietly on the orderliness of the very first moment. Let yourself settle a little more deeply now. There is nowhere to go, nothing to hold, nothing to work through. Let the weight of your body ease into the surface beneath you, and let your breath find its own unhurried rhythm, slow, even, and completely effortless. Each thought that rises can simply drift away, like a leaf carried off by a current you cannot see. You are here, you are still, and the whole vast universe is quietly holding you as you rest. Some physicists have come to believe that time itself is not a fundamental ingredient of the universe, but something that emerges from a deeper process, specifically from the phenomenon of quantum entanglement. In this view, what we experience as the flow of time is a consequence of the way quantum systems become correlated with one another, weaving a sense of sequence and change out of relationships that at the most basic level exist all at once. Time, in this picture, is less like a river and more like warmth, a quality that arises from the behavior of many parts together, not something built into the fabric from the start. The Page-Wooders mechanism, developed by physicists Don Page and William Wooders in the early 1980s, offers a precise and quietly beautiful way of understanding how time can emerge from a universe that is, at its deepest level, entirely timeless. In their framework, the universe as a whole exists in a static quantum state, with no time at all, but an observer inside that universe becomes entangled with a kind of internal clock, and through that entanglement, the experience of change and duration arises. Time, in this sense, is something that happens between parts of the universe, not something the universe exists within. It is a relationship, not a backdrop. Causal dynamical triangulations is a research program in quantum gravity that takes a remarkably concrete approach to one of physics' most abstract questions: how space-time itself can emerge from something more fundamental. Rather than assuming a smooth, continuous fabric of space and time from the outset, this approach builds space-time from the ground up, assembling it computationally from vast numbers of tiny, discrete building blocks and allowing the geometry to take shape through the mathematics of quantum probability. The result is a kind of cosmic architecture that grows organically from simple rules, the way a complex and intricate structure can arise from endlessly repeated elementary steps. In causal dynamical triangulations, space-time is assembled by gluing together an enormous number of tiny building blocks called simplices, the higher dimensional equivalents of triangles and tetrahedra, each one a small, flat, elementary piece of geometry. The key insight is that the gluing is not arbitrary. It must respect causality, meaning the way the pieces fit together must always preserve a consistent direction for time. From this single, quiet constraint, the large-scale structure of a curved and expanding spacetime can emerge, the way the smooth curve of an arch emerges from the careful placing of individual stones. When physicists run the simulations at the heart of causal dynamical triangulations, something quietly remarkable emerges from the mathematics, a universe that spontaneously organizes itself into 4 dimensions, 3 of space and 1 of time, just as we observe. The simplices do not need to be told to produce this structure. It arises on its own from the rules of the calculation, as naturally as a smooth surface emerging from countless tiny facets. The fact that a 4-dimensional universe falls out of such a spare and minimal framework is, in its own understated way, one of the more striking results in modern theoretical physics. Asymptotic safety is a program in quantum gravity developed largely by Steven Weinberg, built around a precise and hopeful idea that gravity, rather than breaking down completely at the highest energies, may instead settle into a well-behaved, self-consistent state where its quantum behavior becomes controlled and finite. In ordinary approaches to quantum gravity, calculations at extreme energies produce infinities that cannot be removed, but asymptotic safety proposes that gravity possesses a special point in its mathematical structure, a fixed point, where those infinities are tamed. It is a vision of physics that remains coherent all the way to the very beginning of the universe. Within the framework of asymptotic safety, the singularity at the Big Bang, that point where classical physics breaks down entirely and density becomes infinite, may simply dissolve. As the energy scale approaches the fixed point that asymptotic safety predicts, the effective behavior of gravity changes in a way that prevents the singularity from forming at all, replacing it with a smooth and finite transition. The beginning of the universe, in this picture, is not a breakdown of the laws of physics, but a place where those laws quietly transform into something deeper and more complete, a threshold rather than an edge, a doorway rather than a wall. The amplituhedron is a remarkable geometric object discovered by Nima Arkani-Hamed and Jaroslav Trunka that may lie beneath quantum field theory in a way that requires no space-time at all. In ordinary physics, calculating how particles interact demands enormous laborious work within the framework of space and time. But the amplituhedron encodes those same interactions as the geometry of a multidimensional shape, a single, elegant form whose volume, when computed, gives the answer directly. The mathematics is spare and luminous, suggesting that space-time itself may be a kind of shadow cast by something more fundamental and more beautiful. Some theorists now propose that space and time, the very stage on which all of physics has always been performed, are not fundamental ingredients of reality, but emergent properties, the way temperature emerges from the motion of countless molecules, or the way a smooth shoreline emerges from the arrangement of individual grains of sand. In this view, asking what happened before the Big Bang may be like asking what lies beneath the surface of a lake. The question assumes a depth that may not exist in the way we imagine. Space and time, in this picture, are late arrivals, woven together from something quieter and more primary that has no location and no duration of its own. Quantum information theory, the study of how information is stored, transmitted, and transformed at the quantum level, has quietly moved to the center of some of the deepest thinking in modern physics, with a growing number of researchers proposing that it may be the true foundation from which spacetime itself is woven. In this framework, the geometry of space, the distances between points, the curvature of the universe may be a reflection of patterns of quantum entanglement, the way a tapestry's image is carried, not by any single thread, but by the relationships between all of them. The universe in this vision is less a place and more a vast, intricate conversation between quantum states, and space-time is what that conversation looks like from the inside. There is no need to hold on to any of these ideas right now. Let them drift away like mist over still water. Feel the weight of your body resting where it is, fully supported, fully at ease. Let your breath move slowly, without effort, in and out. With each slow exhale, release a little more of the day. Your thoughts may wander, and that is perfectly fine. Simply let them pass through, like clouds moving across a wide and unhurried sky. You have nowhere to go. There is nothing to figure out. Just rest here, gently, in the quiet. Conjecture known as air equals aper, proposed by Juan Maldacena and Leonard Susskind in 2013, draws a profound and quietly astonishing connection between two phenomena that once seemed entirely unrelated, wormholes and quantum entanglement. A wormhole, in general relativity, is a tunnel connecting two distant regions of spacetime. Quantum entanglement links two particles, so that measuring one instantly affects the other, regardless of distance. The conjecture suggests these are not merely analogous but the same thing, described in two different languages, that whenever two particles are entangled, they are, in some deep geometric sense, connected by a microscopic bridge through space. Building on the air equals aper conjecture, some theorists have proposed something even more extraordinary, that the wormholes connecting distant regions of space are not just related to quantum entanglement, but are literally constructed from it, woven together by the invisible threads linking entangled particles. In this picture, the fabric of spacetime itself is stitched together by entanglement, the way a cloth is held together by the countless crossings of its threads. Remove the entanglement, and the fabric tears, strengthen it, and the geometry of space becomes more connected and more real. It is a vision in which the relationships between quantum particles are not merely occurring within space, but are, in a very direct sense, the reason space exists at all. Some models in quantum gravity suggest that what we call the Big Bang, that moment of origin from which our universe expanded, was not a beginning from nothing but the culmination of a prior phase, a quantum geometry that had been slowly, quietly collapsing. In these scenarios, the universe before the Big Bang was not a classical spacetime, but a diffuse, wave-like structure of quantum geometry, contracting and concentrating until it reached the conditions that sparked the expansion we now trace backward through cosmic history. The Big Bang, in this reading, is less a creation and more a transformation. The moment a long inward breath became an outward one. Roger Penrose, one of the most original minds in modern physics, developed a framework called twistor theory, beginning in the 1960s, as a radical reimagining of the foundations of physics, one in which space-time is not the primary arena but a derived structure, emerging from a more fundamental mathematical space built from objects called twistors. In twistor space, the basic entities are not points in space and time, but rays of light, the null lines that trace the paths of massless particles. Penrose envisioned a world where the geometry of light itself is the bedrock, and the familiar four dimensions of space and time are a kind of projection from that deeper luminous foundation. Spin-foam models are an approach within loop quantum gravity that attempt to describe the quantum geometry of space-time at the very smallest scales, at the Planck scale, where the familiar smooth fabric of space and time gives way to something granular and discrete. In a spin foam, the history of the universe is not a smooth continuum, but a vast branching network of quantum transitions, each one a tiny step in the evolution of geometry itself. The model gets its name from the foam-like structure of these networks, which represent the quantum states of space and time, the way a film of soap bubbles represents the geometry of surfaces, intricate, delicate, and built from the simplest possible pieces. There is a possibility, held quietly at the frontier of physics, that the universe did not emerge from a physical substance or a prior space-time at all, but from a network of quantum information, a web of relationships and differences that has no material substrate, no location, and no duration, yet contains within its structure everything needed for space, time, matter, and light to arise. In this vision, the universe is, at its most fundamental level, not a thing but a pattern, not a place but a kind of knowing, a vast and self-consistent arrangement of information from which the richness of all we observe has slowly, quietly unfolded. And somewhere within that unfolding, on a small and unhurried world, you are resting now. Some theorists propose that mathematical structures themselves are the ultimate reality underlying all of physics. In this view, the universe does not merely follow mathematical laws. It is a mathematical structure, as real and complete as any theorem, existing not in space or time, but in the timeless realm of pure form. The physicist Max Tegmark called this the mathematical universe hypothesis, suggesting that every consistent mathematical structure exists somewhere, and our universe is simply one of them. It is a thought that settles the mind rather than unsettles it, the idea that beneath all the noise and motion of existence, there is something as serene and unchanging as a geometric truth. The Hartle-Hawking state is a proposal in quantum cosmology that assigns a quantum amplitude, a kind of probability weighting, to each possible geometry the universe could have. Rather than describing a single history of the cosmos, it describes a superposition of all possible cosmic shapes, all possible ways space-time could have been arranged, each one weighted by how likely it is to arise from the quantum rules of gravity. The universe we inhabit is not the only possible universe in this framework. It is simply the one whose geometry carries the greatest weight in that vast, still sum over histories. There is something deeply restful in that image, not one rigid path, but a gentle, probabilistic unfolding. Pre-Big Bang cosmology in string theory posits that before the expansion we know, the universe passed through a contracting stringy phase, a long, slow period of compression governed by the exotic physics of strings rather than classical matter. In this picture, the Big Bang was not a beginning but a turning point, the moment a universe that had been drawing inward finally reversed and began its long outward journey. The stringy phase before the bang would have been a world of very different physics, where the fundamental constituents were not particles, but tiny vibrating filaments of energy, weaving through dimensions we cannot directly perceive. It is a vision of the cosmos as endlessly patient, contracting, pausing, and then breathing outward again. The dilaton field plays a central role in pre-Big Bang string cosmology, acting as a kind of engine that drives the expansion of the early universe. The dilaton is a scalar field that arises naturally in string theory, and in pre-Big Bang models, it grows steadily stronger as the universe contracts, storing energy that is eventually released as the bang itself. It is a field with no direct analog in everyday experience, invisible, pervasive, threading through every point in space, yet in these models it is the quiet force that wins the cosmic spring before the universe uncoils. The light entering your eyes from the farthest stars we can see traveled for billions of years through a universe that was set in motion, in part by this unseen and ancient field. Let your body grow a little heavier now. Let your shoulders settle, your hands open, your jaw soften. There is nowhere to go and nothing to remember. Each breath carries you a little further from the day and a little deeper into stillness. The questions of the cosmos can rest for now. They have been resting for billions of years, and they will still be there, patient and unhurried, when the morning comes. For now, there is only this: the slow rise and fall of your breathing, the warmth of wherever you are lying, and the vast, gentle dark that holds everything, including you, without effort. Fred Hoyle, one of the most creative and contrarian minds in 20th century astronomy, proposed in 1948 a model of the universe called the steady-state theory, a cosmos with no beginning and no end, where matter is continuously created to fill the space left by expansion, and the universe looks the same at all times and in all places. For Hoyle, the idea of a singular explosive origin was philosophically unsatisfying, and he famously coined the term Big Bang as a dismissive label for the competing theory, a name that, ironically, stuck. The steady-state universe is a serene image in its own right, an eternal self-renewing expanse with no birth and no death, simply enduring. The steady-state theory, elegant as it was, could not survive the discovery of the cosmic microwave background radiation in 1965. That faint, uniform glow filling the entire sky was precisely what a hot, dense early universe would have left behind, and precisely what a steady-state universe with no such origin could not produce. The evidence was quiet but decisive, a whisper from the distant past that spoke clearly enough to change the course of cosmology. Most scientists set the steady-state model gently aside, not with hostility, but with the calm recognition that the universe had answered a question, and the answer pointed elsewhere. Plasma cosmology is an alternative framework, developed primarily by the Swedish physicist Hannes Alfvén and later extended by others, that attempts to explain the large-scale structure of the universe through the behavior of plasma and electromagnetic forces rather than gravity alone, and that rejects the idea of a Big Bang origin entirely. In this view, the universe is ancient beyond any measured age, shaped by vast electric currents and magnetic fields threading through the cosmos on scales we are only beginning to map. It remains a minority position held by a small number of researchers working outside the mainstream of cosmological science, but it reflects the enduring human desire to imagine a universe without a beginning. Plasma cosmology, while imaginative, has not been able to generate the precise, testable predictions that modern observational cosmology demands. It does not account for the observed abundances of light elements formed in the early universe, nor does it reproduce the detailed pattern of temperature variations in the cosmic microwave background. For these reasons, the overwhelming consensus of working cosmologists is that plasma cosmology does not offer a viable alternative to the standard model. It is mentioned here not to cast doubt on what we know, but as a reminder that science is a living process, one that tests every idea against the quiet, patient testimony of evidence. And so we arrive, at last, at the question that underlies every model, every equation, every theory we have gently explored together tonight. Why is there something rather than nothing? It is the oldest question in philosophy and the deepest in physics, and it remains, honestly and beautifully, unanswered. No theory yet devised can reach behind the existence of the universe and explain why anything at all should be, why the quantum laws exist, why mathematics applies, why there is a something from which a universe could ever arise. The question does not demand an answer tonight. It asks only to be held, the way the night sky holds its stars, openly, without urgency, in a stillness that is its own kind of answer. The philosopher Gottfried Wilhelm Leibniz first posed the question of why there is something rather than nothing in 1714. In a short philosophical essay, he asked what may be the simplest and yet most bottomless question a human mind can form. Why does anything exist at all? He was not expecting an answer so much as opening a door that has remained open ever since, swinging gently in the wind of every cosmological theory that followed. That question, posed by a man with a quill and candlelight more than 300 years ago, still echoes through the most advanced equations physicists write today. Some physicists argue that absolute nothingness is inherently unstable and must, by the laws of quantum mechanics, fluctuate into something. In this view, a true and total void cannot simply rest. It is restless at its very foundation, trembling with latent possibility, the way a perfectly still pond will eventually ripple from the faintest breath of air. Quantum mechanics does not permit perfect stillness, and so even the deepest emptiness carries within it the seed of something. The universe in this picture was not so much created as inevitable, a quiet inevitability written into the nature of nothing itself. The physicist Lawrence Krauss brought this idea to a wide audience with his book published in 2012, arguing that the universe could have arisen naturally from a quantum vacuum without the need for any external cause or creator. His work was accessible and warmly written, and it reached far beyond the walls of university physics departments. Scientists continue to debate the precise meaning of his argument, whether the quantum vacuum truly counts as nothing, or whether it is already something. But the conversation he opened remains one of the most thoughtful and widely shared in modern cosmology. He reminded many people that the deepest questions are not locked away in equations alone. A quantum vacuum is not truly nothing. It is a sea of fluctuating quantum fields, alive with ceaseless, invisible activity even in the absence of any particles or matter. Virtual particles flicker in and out of existence at every point in space, borrowing energy from uncertainty and returning it so swiftly that no instrument can hold them still. The quantum vacuum has measurable effects. It shifts the energy levels of atoms in ways scientists have confirmed with extraordinary precision, and it exerts a tiny but real pressure between closely spaced surfaces. What we call emptiness at its deepest level is not empty at all. It hums with a kind of foundational aliveness that has no equivalent in ordinary experience. And yet, even with all of this, the equations and the models, the bouncing universes and the tunneling geometries, the timeless wave functions and the flickering quantum fields, the true meaning of the word nothing before the Big Bang may be forever beyond the reach of human comprehension. Our minds grew up inside time, inside space, inside a universe that already existed. We have no faculty for imagining the complete absence of all of it. No framework, no language, no picture that reaches all the way down. And perhaps that is not a failure. Perhaps it is simply the shape of the horizon, the place where the light of understanding softens and dissolves into something wider and more restful than knowledge. You have traveled a long way tonight, from the first moments of the universe, through its deepest theories, all the way to the edge of what can be known and a little beyond. You have held the largest questions a human mind can form, and you have held them gently in the quiet of this hour without needing them to be resolved. The universe is vast and ancient and still unfolding, and you are woven into it, made of the same hydrogen forged in its earliest moments, breathing air shaped by billions of years of patient becoming. Tonight, let all of that rest. Let the questions drift like distant light, unhurried and unheld. The mystery is not going anywhere. It will be here tomorrow, patient and luminous, as it has always been. For now, there is only the warmth of this moment, the softness of your breathing, and the deep, unhurried quiet of a universe that has been here all along, holding you without effort or end. Sleep well. Good night.